Okay, on this video, we're going to finish this unit on leak detection, system evacuation, system cleanup. On page 199, let's talk about system evacuation. Get some of these terms, learn some of these terms. They're on your term sheet and your study guide today. What is the purpose of an evacuation on page 199 in your textbook? Refrigerant systems are designed to operate with only refrigerant and oil in them. Those two things. That's how they're designed, nothing else. Refrigerant and oil. When systems are assembled to service, air enters. Air contains what? Air contains oxygen, nitrogen, hydrogen, and water vapor. Removing air and other non-condensables, remember, nitrogen is a non-condensable, so it's not going to work in our refrigeration system. They will cause a rise in the system's head pressure. If it gets in the condensing unit and it doesn't condense, it's taking up space where the condensing usually happens. And because it's not condensing, the head pressure is rising because you're not releasing heat from the system. So it's a non-condensable, okay? Latent heat of condensation is not taking place. Now look at this. Removing the air and non-condensables from the system is called degassing. Removing non-condensables and gassing from the system is called degassing. We're under the header evacuation, the term degassing. Next, removing water vapor from the system is called dehydration. So you have degassing, removing non-condensables, and removing water vapor is called dehydration. Now, when you remove both of them together, we have an evacuation, okay? So, oxygen, hydrogen, water vapor have a chemical reaction in the system which produces acid. Acids deteriorate the system components, including copper. So oxygen, hydrogen, water vapor react in the system. So what do we know so far? Chemical combinations create hydrofluoric and hydrochloric acids in the system. Evacuation is degassing plus dehydration. Okay? Now your book says on page 200, when water vapor becomes entered into the system, it becomes an acid. Okay? Becomes acid. Now what happens when you have all of these together? On page 200 in your book it says, you create something called sludge. After acid forms, you don't run a good evacuation. You don't dehydrate with a low enough vacuum, and guess what? You leave moisture in the system. That becomes an acid. What happens next? When acid forms, the motor windings deteriorate, metal corrosion, and sludge starts to form. Sludge is a tightly bound mixture of moisture plus acid plus oil. You need to learn these for your EPA exam. You need to learn them for my exam this Friday to get through this course. Degassing and dehydration equal evacuation. Moisture plus acid and oil equals sludge in the system. This can cause the components to become plugged. Proper evacuation can eliminate the formation of acid and sludge. Okay, and that's on page 200 in your book. To avoid corrosion and sludge problems, moisture must be kept out through good service practices and effective preventive maintenance. The only sure way is through a high vacuum pump. But once sludge is formed, standard cleanup procedures involving oversized dryers are designed for this. All right, now these dryers that are good for high acid and all, they'll even say it on the liquid line dryer and the suction line dryer. Now, what is evacuation in theory? Okay, let's talk about evacuation in theory. The theory of evacuating a system, to pull a vacuum means to lower the pressure in the system below atmospheric. How simple is that? If we get the pressure in the system below atmospheric, it's in a vacuum. If we lowered the pressure below atmospheric here and you got in a vacuum, you wouldn't be able to breathe in air. This is normally at a pressure below atmospheric, which is 14.696. Okay? Now, atmospheric pressure plus gauge pressure equals what? PSIG, whatever's inside your system. All right? Degassing, remember, moves non-condensables. Systems should be evacuated from the high and the low sides of the system. They're connected. If you have a service valve of a suction line and a liquid line, and they're open, and you're running a vacuum, you should be able to pull a vacuum through the whole system. Okay, low and high side and everything should be pulled down in a vacuum. That's what your book's saying. Now we measure the vacuum in microns, M-I-C-R-O-N-S. Microns. 1 micron equals 1/25,400th of an inch. It's 1/1000th of a millimeter, but it's 1/25,400th of an inch. That's pretty small. Okay, this is on page 200. Now your blue gauge on your set of gauges, your red and blue gauges, your blue one's called a compound gauge. Just like a compound word, foot and ball becomes foot and ball. On a compound gauge, you have positive pressure reading and a negative pressure reading. So the compound gauge not only reads low pressure on the low side in the PSIG, it also goes backwards and reads into a negative vacuum. It's often used to measure a vacuum level. The gauge starts at 0 and reduces to 30 inches vacuum. Okay, so that's on page 200. Now, let's go to page in your book, page 206. The vacuum pump is with your tool that you'll get to pump it down. We want it to 500 microns. That's the industry standard. When you get down to 500 microns, you can be confident that you've removed all non-condensables and what? Dehydrated the system. Degassed it and dehydrated it. And at 500 microns, you've evacuated the system. Guys, this is the terminology you need to start speaking in the field so people can understand you. Okay? Now, what is a deep vacuum? Here's a new phrase for you on page 206. What is a deep vacuum? A deep vacuum is this. Anytime you reduce the system from 250 to 500 microns, so you're getting below. When the vacuum reaches the desired level, you can valve it off. If it starts to rise, you may have water still boiling in the system. Now, it could also mean that it's still coming out of oil in the crankcase. You can lightly tap it with a small hammer to make it come out. So that's a deep vacuum. You don't want to pull it down too low. If you pull it down too low, you can actually start boiling the oil. And that's not good. So just below 500 is good. What is a multiple or triple evacuation on 207? And how do you do that? Well, that's in your lab manual, and you will be doing that in the lab. You will run a triple vacuum in the lab. All of this we're talking about, you will do hands-on. This is used by technicians to get to a deep vacuum. So what do we do here to get to a triple vacuum? Normally accomplished by getting to 1500 vacuum, okay? You get down to 1500. Is that on here? Let's see. Here's some different pictures right here of vacuum gauge tools that we use in the field. You will get one of these on your grad kit. There's your blue compound gauge hooked up to it. I get all of you to learn how to do that right from the beginning. You all start learning how to run vacuum as soon as you come here, don't you? There's your deep vacuum measured in 250 to 500 microns. Okay, now remember, all of this is on your MCC course, this PowerPoint, so you have access to all of this. Evacuating the system to a low vacuum is 1500 microns, okay? Then you allow a small amount of dry nitrogen into the system at 1500 microns. That dry nitrogen will absorb moisture and let it bleed out of the system. Then you run it again and reduce it to 1500 microns. And once again, you bleed it with some nitrogen. Then you go down after the third time to about 500 microns. And you let it hold for 15 to 20 minutes. The following is a detailed description of a triple vacuum, the latter being performed 3 times is called a triple vacuum. Doing it twice is a multiple. But that's a really good vacuum if you run a triple like that. Breaking it with nitrogen, that's how you do that. Now on 209, what did we say? If you look on picture 209, leak detection. If you run a vacuum and it's saying you get down to 250 to 500 microns and you start going back up, guess what? You may have a leak. Now we'll tell you this, normally if you can't get below 750 microns, you probably already got a leak because you're pulling too much air in the system somewhere. You won't get a good deep vacuum if you're pulling air in the system. But if your needle starts rising back up, or your microns start going up on your digital scale, you may still have a consistent rise, not just a little bit of rise and then it stops because it found some moisture and got out of it. I'm talking about one that keeps on going. You got a leak. Now we'll tell you this, just because you found a leak like that does not mean that's the way you detect leaks. That's a byproduct of running a vacuum and found a leak like that. That's not how you search leaks. You have to fill with dry nitrogen and check all your braze joints and flat joints. That's the proper way. Now, let's say you have moisture in the system and you want to remove it. One way to dehydrate it is to get a good liquid line dryer on there with moisture removal. And remember this, we do sublimation on page 210. The process of turning a vapor without passing into a liquid is called sublimation. So anytime you have ice in your system and it turns straight into a gas, that's sublimation. That happens from pulling a quick vacuum. But we have moisture in the system. Let's say we have water in the system and we want it out. The very first way you're going to do that is running a vacuum. The vacuum will, by lowering the pressure, will boil the moisture, the water, into a gas and pull it out through your vacuum pump. By lowering the pressure below atmospheric, you can boil it without heating it. So wherever the water is at in your system will come out. If there was by chance some left in there, that's why you have a liquid line dryer on the system. It also protects you in case somebody gets moisture in the future in the system in it. You'll have a liquid line dryer with some desiccant material that'll absorb that. Okay, so then we go to page 219 in your book. Cleaning a dirty system. Well, sometimes a compressor could have a burnout and it'll short. And I'm going to give you handouts in the classroom on how to clean this out and the proper procedure. So we know heat and refrigerant and moisture create acid, moisture, acid, and all create sludge. They do have filter dryers for burnouts, including a suction line dryer that's used to clean it out. I was trained that if you put a suction line dryer on a system and a liquid line dryer after burnout, you have to get an HH dryer, it'll say -HH, high acid dryer, and you leave it on the system. You come back between 24 and 36 hours, you put another dryer on there. Okay? You check the refrigerant in it with a little leak test like this. See that? If it's yellow, it's good. If it's orange, it's not. All you have to do is take this little plastic thing right here, put it on your core. Psh, the gas will shoot right across that cardboard and let you know if you have acid or not in the system. Okay, that's called a quick check. You could do that in a lab. Okay, you could do that in a lab. Another way is, you have to, and another thing is you take those dryers off and you have to keep putting them back on until all the acid's gone. Another thing is you see that sight glass right here? That sight glass in the middle has a little colored piece of cardboard. On this one, it's yellow. When it's yellow, it's wet. When you run a vacuum and it turns green, see how it says green on there? And it turns green, and you can see it in your book. Since your book's open right now, just look down. There it is. When it turns green, it means you got a good vacuum. There's no more moisture in the system, but still go by 500 microns. Okay, so there's different little ways you could tell about them burn-ups and them cleanups. So if y'all have any more questions about this, you can call me or text me, and I'll talk to you about it, okay? So that's how you do that. Leak detection while in a vacuum, we talked about that. General evacuation procedures, Schrader valves. Remember, Schrader valves are those little bitty valves like you see on a tire in the tube, and you press that little core. That little core, when it's depressed, it allows the gas to go back and forth. Actually, when you're running a vacuum, you should pull that out, because that little core inside your Schrader valve, it's got to be depressed to allow the vacuum to happen. Well, that little core is taking up a lot of room in your valve. It actually acts like a restrictor. It makes you take a lot longer time with a vacuum. And then you should put them back after you're done. Okay? Then we talk about your gauge manifolds. Now let me ask you this. What kind of hose should you have to run a vacuum? Well, a vacuum works best with a bigger hose. So the bigger the diameter hose, the more vacuum and the quicker vacuum you can run. Of course, with a long hose, it would take a longer time. A longer hose and a smaller diameter acts like a restrictor. Takes a longer time. So what's the quickest way to run a good vacuum? A hose with the smallest diameter and the shortest run. The thickest, biggest diameter hose with the smallest run gives you your quickest vacuum, okay? Using dry nitrogen, if you read it here, they have some points. It doesn't matter if you release the nitrogen to the atmosphere. The EPA doesn't care, because the atmosphere is already 78% nitrogen. That's fine. Never start your system when it's pressurized with nitrogen. Why? Because your compressor is not supposed to run on nitrogen. It's refrigerant, which has what? Oil in it to lubricate it. If you try to run a system while it's under nitrogen, you could destroy your compressor. If you run it while it's in a vacuum, you will burn up and destroy the compressor. Why? Because it was meant for refrigerant and oil. So never run a compressor or turn on the system while it's got nitrogen in it or it's under a vacuum. All right, and how to clean a dirty system, that's in there. Remember, when you go up to a unit with a burnout, those fumes can be toxic, they're nasty. Wear safety goggles and gloves. And then you have your summary. All right, students, let me know if you have any questions.